Hey everybody, Janae's here. Can y'all hear me? Hold up. I don't know if you can see me. All right. So, hello to you guys, gals, peoples. So today I will be reviewing for Heat and Physics 100. So please join in. I'm just going to go through the slides. And I'm doing this live so I can stay awake because I'm feeling tired and I have a quiz later today at 12:30. So I want to be prepared. So I need your help. I need your eyes and ears. Feel free to type in the chat if you want to say something. I can start by saying hello. So if you can see that, I just put hello in the chat. Feel free to chat back. I'm going to get started here. So I am not able to share my screen with you, but if you listen, you should be fine. So heat, the drop of water has less internal energy than the cup of water. So one drop of water has less internal energy than the cup of water. The drop of water has fewer molecules than the cup of water. So the drop of water has fewer molecules than the cup of water. And the drop of water has less kinetic energy than the cup of water. So a drop of water has less internal energy, less molecules, and less kinetic energy. Specific heat capacity. So everything absorbs heat energy at different rates. So a pie, for instance, the crust of the pie will cool much faster than the actual filling of the pie. It would be much hotter and it will cool a lot slower than the crust. But everything absorbs heat and energy at different rates. It takes longer to warm the water than the pot. So if you put an iron pot on the stove, it's going to take longer for the water to warm than it would for the pot. So water has a higher specific heat capacity than the pot. So water has a higher specific heat capacity than the pot. Specific heat capacity of any substance is that the heat energy needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. So units of specific heat capacity are J divided by kg divided by degrees Celsius, or cals divided by gram divided by degrees Celsius. So specific heat capacity of any substance is that the heat energy needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. So low and high heat capacities. 1 kg of gold and 1 kg of aluminum. It takes gold to heat 1 kg of gold 7 times faster than it takes aluminum to be heated. 1 kg of aluminum. So it takes gold 7 times faster to heat 1 kg of gold than it takes aluminum. Gold has a low heat capacity. Aluminum has a high heat capacity. The specific heat capacity for aluminum is more than twice that of copper. So if equal quantities of heat are given to equal masses of aluminum and copper, the metal that more rapidly increases in temperature is copper. So specific heat capacity for aluminum is more than twice that of copper. So if equal quantities of heat are given to equal masses of aluminum and copper, the metal that more rapidly increases in temperature is going to be copper. So aluminum is more than twice that of copper. Hot sand cools off faster at night than plants and vegetation, which indicates that the specific heat capacity for sand is low, so less than that of plants. Hot sand cools off faster at night than plants and vegetation. Specific heat capacity uses and examples of high specific heat capacity of water. So examples of high specific heat capacity of water. A car cooling system is an example. So in a car cooling system, you have your air conditioning, you have your thermostat, your water pump, your radiator, your airflow, your heated airflow. To say that water has a high specific heat capacity is to say that water requires a lot of energy in order to increase in temperature. Water gives off a lot of energy in cooling, and water absorbs a lot of energy for a small increase in temperature. So it requires a lot of energy in order to increase the temperature of water. And it requires a lot of energy in cooling, or it gives off a lot of energy in cooling. So it takes a lot of energy to increase its temperature, and then water gives off a lot of energy in cooling. And it absorbs a lot of energy for a small increase in temperature. So again, reiterating that it takes a lot of energy to increase its temperature, which would cause the temperature of 50 cubic centimeters of cold water to change the most 50 grams of copper at 90 degrees Celsius, or 50 grams of water at 90 degrees Celsius. explain that answer. So which would cause the temperature of 50 cubic centimeters of cold water to change the most? 50 grams of copper at 90 degrees Celsius, or 50 grams of water at 90 degrees Celsius. So we know it takes water a longer time to heat. It takes copper a least amount of time to heat. So that's going to get hotter faster. So the 50 grams of copper would change the most. So reading the question again, which would cause a temperature of 50 cubic centimeters of cold water to change the most? 50 grams of copper at 90 degrees Celsius, or 50 grams of water at 90 degrees Celsius. The correct answer is water. The correct answer is water. Right? So most substances expand when they are heated. Molecules gain energy, move faster, and need more space. So most substances contract when they are cooled. Molecules lose energy, move slower, and take up less space. Read that again. So most substances contract when they are cooled. Molecules lose energy, move slower, and take up less space. Which expands most for a given temperature rise? Solid, liquids, or gases? Which expands most for a given temperature rise? Gases is the correct answer. The fact that gasoline will overflow from an automobile tank on a hot day is evidence that the expansion of gasoline is more than the tank material. Is it better if a door lock and its key are made of the same material? Why or why not? Yes, it is better for a door lock and key to be made of the same material because they can both expand at the same rate. Thermal expansion of water. What do ice cubes and broken water pipes tell us about water? So, what do ice cubes and broken water pipes tell us about water? So water expands as it freezes. So you might get a burst pipe. Hopefully that doesn't happen, but it does. It expands when it freezes, and it could potentially burst. As water cools, it contracts until the temperature has fallen to 4 degrees Celsius. From 4 degrees Celsius down to 0 degrees Celsius, the water expands. As ice cools, it contracts. So there's an H2O liquid and an H2O solid. The liquid, you could see the molecules are close together. And then you can see them kind of expanding when they get solid. They expand. So water at 4 degrees Celsius will expand when it is slightly cooled and warmed. So water at 4 degrees Celsius will expand when it is slightly cooled and warmed. So 4 degrees Celsius will expand. Why does the ice float on water? Because it's less dense. It's more spread out because water expands as it freezes. So what are the temperatures for freezing water and boiling water on the Kelvin temperature scale? So freezing water on the Kelvin scale is going to be, I want to say 0 degrees. And then what will boiling water be? I want to say 273 degrees Kelvin. Why do substances expand when temperatures increase? Why do they expand? So we know water expands when it freezes. We know that different materials will expand. Like copper. Copper expands. All right, y'all are doing well. Do we have, let's see, 18 minutes here? Feel free to write in the chat. Don't be hesitant about that. I'm going to go ahead and go to the next slide here. We're going to talk a little bit about heat transfer. So heat is the topic of the day. So heat transfer. So conduction, convection, and radiation. How y'all doing out there? Y'all okay? Okay, so review questions. What are the temperatures for freezing water and boiling water on the Kelvin temperature scale? So freezing water is 0 degrees Celsius and 273 degrees Kelvin. And then boiling water is 100 degrees Celsius and 373 degree Kelvin. Why do substances expand when temperature is increased. So molecules have more energy. That was the answer. Molecules have more energy. So we know when molecules have more energy, they're going to expand. And they're going to be warmer. So the temperature is increasing, it's getting warmer. The energy, kinetic energy, is expanding. The molecules actually get smaller. It becomes less. Molecules have more energy. All right, so distinguish between temperature and heat. So temperature and heat. So heat transfers of energy at different temps. Temperature is the average kinetic energy. So distinguish the difference between temperature and heat. Heat transfer of energy. Heat transfer of energy. Temperature is the average kinetic energy. So heat is going to transfer the energy. So different temps transferring energy, and temperature is the average kinetic energy. So does a substance that heats up quickly have a high or low specific heat capacity? Does a substance that heats up quickly have a high or a low specific heat capacity? So if it's heating up quickly, it's going to have a low specific heat capacity. So then if it doesn't heat up quickly, then it's going to have a high specific heat capacity. So conduction, most effective in solids where molecules are held together and heat is transferred when atoms bump into each other. So conduction is most often in solids where molecules are held together and heat is transferred when atoms bump into each other. So that's conduction. Again, it's most effective in solids where molecules are held together and heat is transferred when they bump into each other. Conductors allow heat to pass easily. So they have loosely held electrons, which can transfer heat energy through the material. Examples are copper, silver, and most metals are good conductors. So think of a copper pan as a good conductor. So if there's water in that copper pan, you put it on the stovetop, which is going to heat quicker, the copper or the water, the copper is going to heat quicker. The copper has a low capacity for heat. It's going to heat much quicker. It's a good conductor. So metal branding iron and car radiators, air conditioners, refrigerators, and freezers. Those are also good conductors. I hope this is making sense. So conduction, so insulators do not allow heat to pass easily. So examples of an insulator is snow. If you've ever seen like a snow cave, that's a really good insulator. Wood is a really good insulator. Plastic, So I don't know if you all put plastic in your windows when it starts to get cold. That's a good heat conductor. Most gases are good heat conductors. So if you've seen like a house and maybe like there's still snow on top of the rooftop, but like if you take a look at the garage and you might start to see the shingles and you see the snow isn't really on the roof where the garage is, maybe it's like melted off. Well, that's because the garage may be insulated. I'm sorry, the garage would not be insulated, but the house will be insulated. Seems like, well, we said that like a snow is a good insulator. Yeah. That's kind of tricky. I get to think of that. Let's read it again. So it says insulators do not allow heat to pass easily. So in the garage, you might have heat that's passing easily. Like if you have your garage connected to your home, well, the heat is passing easily. It's not like insulated. It doesn't have the insulator in the inside. And so heat is escaping on the outside and it's causing the snow to melt on the rooftop. So then you'll be able to see the shingles. Does that make sense? I hope so. Thermal conduction has most to do with electrons. A firewalker walking barefoot across hot wooden coals depends on wood's poor condition. I'm sorry, poor conduction. And we said that conduction is like an insulator and it does not allow heat to pass easily. So if a person is walking barefoot across hot wooden coals, so it's going to depend on poor conduction. Problems. So why does a metal door feel cold to touch on a cold day? Well, it's a good conductor. Why do birds fluff out their feathers on a cold day? To trap air for insulation. So heat can be transferred by the fluid itself moving. So liquids to gases. This transmission of heat energy is called convection. So the transmission of heat energy is called convection. So cool air in, warm air out. Convection, most effective in gases and liquids, where the most molecules are free to move. For example, heat a pan of water on a stove, so molecules at the bottom near the heat source gain energy and move faster. So as the speed increases, they move further apart and the density increases. The less dense water is buoyed up and rises to the surface, pushing cooler air down. This is called a convection current. During the day, hot air rises from the land and is replaced by cooler air from the water. So during the day, hot air rises from the land and is replaced by cooler air from the water. At night, warm air rises from the water and is replaced by cooler air from the land. So in either case, warm air, hot air is going to rise. It's going to rise. So in the daytime, the water will come, or the cool air will come from the water, and it will rise, and then it falls. But the warm air rises from the water and replaced by cooler air from the land. So think of the land air blowing back into the water, and it's just a nice cycle. Thermal convection has most to do with fluids. What's convection? Convection. The transfer of heat by the circulation of movement of the heated parts of liquid or gas. So thermal convection has most to do with fluids, liquids, or gas. So when air rapidly expands, it generally cools. When air rapidly expands, it generally cools. So if it's cold, it's going to be more dense. If it's hot, it's going to be less dense. When it's cool, it's going to expand. So
hey, quit studying all the time. I'm sick of you. That's how you be. You be like that.
Oh, there's Danny.
What's up, man?
Hey, Danny. Let's say happy studying to Danny.
She lying. What's up, YouTube? You on YouTube? I'm on YouTube.
I'm sorry, y'all have to ignore my brother.
What is this? School?
Yeah, they're keeping me awake.
Oh, I'm in school now. They keeping you awake.
All right, so when air is compressed, it generally warms. So expand. So when it's cooling, it's compressed. When it's warm. I'm sorry, I have my family around me, y'all.
Ain't even in the picture, girl.
So problems, why is it usually warmer near the ceiling than the floor? So heat rises, it's convection.
Sorry. I'll leave you to it. I'll leave you to it.
Why is the insulation in the attic of a house usually thicker than the insulation in the walls? So heat rises. So it insulates and keeps it inside. Y'all have insulation? So it's warmer near the ceiling than the floor. We talked about heat rising. So heat is going to rise. In the daytime, the warm air rises in the nighttime. The warm air rises. In your home where the ceiling is, the warm air is going to rise. Why is the insulation of an attic of a house usually thicker than the insulation in the walls? Why is it usually thicker? We know that heat rises, and then the insulator is going to keep the heat inside, so the heat wants to escape, but the insulator is like, no, you're going to stay here. You're not going anywhere. So that's what the insulator does. Thermal radiation. Y'all know what that is? So how heat energy travels through space from the sun to the earth. So how heat energy travels through space from the sun to the earth. It's thermal radiation. So it is the only way that heat can travel through a vacuum. Thermal radiation. The only way that heat can travel through a vacuum. From the sun to the earth. The earth is warm during the day by absorbing thermal radiation from the sun. So thermal radiation comes from the sun. It travels from sun to the earth. It's the only way heat can travel through a vacuum, by day absorbing thermal radiation from the sun. So thermal radiation comes from the sun. At night, the earth emits thermal radiation and cools. So to emit means what? To send forth, to release, heat comes from the sun to the earth by the process of thermal radiation. So radiation, emission of radiant energy, everything emits radiation. Everything emits. So to release, to send forth, radiation. What is radiation? We know thermal radiation that travels from space, from the sun to the earth. The only way that heat can travel through a vacuum is going to come through thermal radiation. And we already mentioned that the earth is warm during the day by absorbing thermal radiation from the sun. What will we do without thermal radiation? We'll probably freeze. Yeah. So high temperature objects, the sun, high temperature objects. So it emits energy, waves with high frequency, and it has short wavelengths. So it kind of looks like a zigzag. Or a wave, so like up, down, or like a zigzag. And then the low temperature objects, the people who emit energy. So us people, low temperature objects. Sun is high temperature object. People are low temperature objects. They both emit energy. The sun emits energy and people emit energy. The sun has waves of frequency and people have waves of frequency. So our waves are a little bit longer. They're not as zigzaggy like the sun's, but we do have waves too. Which body emits radiant energy? The sun, the earth, or both? Both. Both emit radiant energy. Everything emits radiant energy. A high temperature source radiates. A high temperature source is going to radiate the shorter wavelengths. So it's more zigzaggy. All right, let's finish. So everything absorbs radiation. Absorption of radiant energy. Everything that emits radiation also absorbs radiation. So everything that emits radiation absorbs radiation. So the sun is going to absorb radiation. People are going to absorb radiation. Everything that emits radiation is going to, in turn, absorb radiation. So a good emitter of radiation is also a good absorber of radiation. So if you're a good emitter of radiation, you're also going to be a good absorber of radiation. If a body absorbs more heat than it emits, its temperature will rise. So if a body absorbs more heat than it emits, the temperature will rise. If a body is hotter than its surroundings, it will emit heat radiation until they are the same temperature. So what's happening? So it's going down, right? If it's hotter and the surroundings are cooler. It's going to emit heat radiation because you flow from heat to cool. And it's going to eventually be the same temperature as its surroundings. So, all right. Radiation. Dull black surfaces are the best absorbers and emitters. Light or shiny surfaces reflect radiant energy and are poor emitters and absorbers. So black is going to absorb energy, and it's also going to emit energy, whereas a light color like gray is going to reflect radiant heat, and it's going to be a poor emitter. So it's not going to emit a lot of energy either, or absorb a lot. But black absorbs a lot, and it also emits. So black is the best absorber and emitter. An object that absorbs energy well also radiates well, emits radiation well. So an object that absorbs energy will also emit radiation well. So black would be one of those things. So a hot pizza placed in snow on a cold winter day is a good net emitter. So think of a hot pizza, think of a cold winter day. Now think of the hot pizza and warmer than the surroundings, and it's emitting more than it absorbs. So it's putting off more than it absorbs. It's emitting more. It's releasing more than it is absorbing. And then it will eventually cool down. It's going to release all of that good energy and it's going to cool itself right on down. So a cool pizza placed in a hot pizza oven is a net absorber. So that's what it's absorbing. So the heat that's from the oven, the pizza is going to absorb all that heat and it's going to get warmer. So it's a good emitter and it's also a good absorber. Problems. So how does heat get radiation? I'm sorry, I gave you the answer. How does heat get from the sun to the earth? So heat gets from the sun to the earth through, we said thermal radiation earlier, so we'll stick with that, thermal radiation. So if two objects in a room are at the same temperature, do they emit and absorb heat energy? So think of two objects that are at the same temperature. So do they emit and absorb heat energy? So yeah, they're going to emit and absorb heat energy. So does the temperature of the objects change? So it doesn't change, but they do emit as much as they absorb. So that's important to know. Convection. Convection is, this is just a recap here, the transfer of heat through a fluid, so liquid or gas, caused by molecular motion. So transfer of heat through fluid. So think of a pot that's being heated. Think of the water boiling and being hotter at the bottom, and then the cool air being pushed in, and then you have this motion going on. So the transfer of heat through a fluid. We talked about a copper pan heating up much quicker than water. So it takes water a longer time to heat than it would take a copper pot that's on a stovetop. And conduction, the transfer of heat or the electric current from one substance to another by direct contact. So conduction, the transfer of heat or electric current from one substance to another by direct contact. And so conduction. And then radiation, energy that is radiated or transmitted in the form of rays or waves or particles. So the sun warms the earth through radiation, thermal radiation. There's waves, there is being transmitted by rays, particles. It's warming the earth through radiation. So direct contact, it would be conduction. So a hot pizza sitting on top of snow, it's going to emit or release the energy of heat, and eventually it's going to cool itself. But that contact, it's what's doing it. That surrounding, it's cooling. The pizza's emitting the heat, and the snow and the coolness is going to absorb that heat. And it can also happen in just the opposite way. If you put a cold pizza in the oven, well, the surrounding is going to be pretty hot. So the pizza is going to absorb that warmth. So the flow is always from hot to cold. It's never cold to hot. Whatever the object that's going to emit, be the one that's emitting the heat. It goes from hot to cool, hot to cold. Never cold to hot. In an external interval. All right. You guys, I just want to look something up really quick. Shout out to Danny. Thank you, Danny. Danny Scotton Jr., thank you so much for telling me happy studying. I appreciate you for getting on there and commenting. It means a whole lot. Thank you, thank you, thank you. I hope you're learning something. Can y'all hear the music? Let me know if you can hear the music. I'm just curious. There should be jazz playing. What? Oh, I'm at monotone. All right, so I'm not finding what I want. One step at a time. Miss Today. All right, it's 11. Oh, it's almost 11. 10:53. How y'all doing? All right, I was just wanting to find something. This is about absorption. So these are just some notes that I have here. It's talking a little bit about radiation and thermal radiation. So it's how heat energy travels through space from the sun to the earth. So we talked about that. So radiation equals the same as the electromagnetic wave. The light that we see is a type of radiation that comes from the sun, like microwaves, radio waves, higher energy, lower energy light, emission of radiant energy. Everything emits radiation. High temperature objects such as the sun emit energy waves with high frequency and short wavelengths. High energy. Low temp objects, people emit energy waves with low frequency and long wavelengths. All right, so absorption of radiant energy. Everything that emits radiation also absorbs radiation. Everything absorbs radiation. Absorption of radiant energy. Everything that emits radiation also absorbs radiation. A good emitter of radiation is also a good absorber of radiation. If a body absorbs more than it emits, the temp will rise. So I'll read that again. If a body absorbs more than it emits, the temp will rise. An example of that, if I absorb more than I emit, whatever I release, if I am absorbing more, then my temperature is going to rise. So if a body is hotter than its surroundings, it will emit heat radiation until they are the same temp. So I'm going to release radiation and I will release heat, and whatever I'm releasing or emitting the heat to, they're going to absorb until they're the same temperature. So dull black surface are the best absorbers and emitters. So a black surface is going to be the best absorber. It's going to be the best to soak up that heat. So if it's a hot day you have on black, guess what? That black that you're wearing is going to absorb a lot of heat. So that's why it's best to wear white in the summertime, because the white is going to reflect the radiant heat. And they're poor emitters, so it's not going to absorb all of that heat. Who I have out there, put your name in the inbox. Feel free to chat with me. So questions, name the 3 ways that heat can be transferred. So heat is transferred through solid, called conduction. Heat can be transferred through liquid, called convection, and heat can be transferred by gas. We call that radiation, radiant radiation, thermal radiation. What's the difference between conduction and convection? So conduction is going to transfer heat between 2 parts of a stationary system caused by temperature differences between the parts. So conduction is going to transfer the parts, and then convection a transfer of heat by the circulation of movement of the heated parts or of a liquid. So a circulation movement. So you can think of a pot on a stove where you have, it's going to be hotter near the bottom of the pot, and then the cooler air will be at the top. So just think about the cool air coming into the pot, going down to the bottom, and then heat rises. So think of it coming back up, and then think of cool air going back down. Think of like a circulation. All right, so what are 3 common ways in which heat is transferred? Conduction, convection, radiation. So how is heat transferred from one place to another by convection? Well, there's a motion, circulation, such as the demonstration I mentioned with the pot, it being hotter at the bottom and then the water rising, and then bringing cool air in, forming the circular motion. In what form does radiant energy travel? Well, it can travel by rays. Think of a sun ray. The sun emits energy to the earth and warms the earth. So that's one way. Another way you think of I want to say a microwave. So we think radiant. So emitting rays of light. Again, the sun shining bright. So in what form does radiant energy travel? And that was the last question there. All right, folks. I'm going to cut the video. I do thank you for tuning in with me. It's been an hour, so it's 11. I do have my quiz at 12:30, so I'm going to go ahead and continue my studies, probably another hour, and then get ready for class. But I do thank you all so much for tuning in. It's been helpful for me reviewing, and I hope that y'all grasp something out of this study session. So thank you so much. Have a good one.